In this video, I'm going to cover basic backpropagation. Before we can jump into it, we need a concept of the important equations. There are four fundamental equations to backpropagation. The first tells us how wrong the activations of the neurons in our output layer are. The second tells us how wrong the activations of neurons not in our output layer are. The third tells us how wrong our biases are, and the fourth tells us how wrong our weights are. With these four equations, we can train our network. In this video, I won't be covering proofs and the more in-depth ideas of why these equations work. Instead, I will simply illustrate how they work. I generally believe an understanding of how is a prerequisite to an understanding of why. I may come back and make another video about the proofs at a later date. We start off where we left off last video. Importantly, we have calculated our Z and A values for our neurons. To begin backpropagation, we initially use our first equation to calculate the error of our output neurons, how wrong they are. The first part of our equation, nabla AC, is the derivative of our cost function. The cost function I am using here is mean squared error, often referred to as the quadratic cost function. The derivative in this case boils down to subtracting our expectation or target outputs from our prediction or actual outputs. The second part of our equation, AZL, is the derivative of our activation function. In this case, we are using the sigmoid activation function. The derivative of the sigmoid function is itself multiplied by 1 minus itself. Sigmoid Z equals A. Thus we can say the derivative of sigmoid with respect to Z is equal to A multiplied by 1 minus A. After calculating these two parts, we then component-wise multiply the two resultant vectors to obtain our error. The component-wise multiplication of two vectors is often referred to as the Hadamard product of two vectors. We have obtained the error of the values of our output neurons. For now, we store this result. As simple as an equation can be, our bias error is simply equal to the error values of our neurons. We store the bias errors. On to our weight errors. The errors of the weights connecting to a layer are equal to the errors of the layer multiplied by the transposition of the activations of the previous layer. We store the weight errors. The final equation to cover is the fourth, which defines the errors in layers other than the output layer. The second term is the same as in the output layer equation. We simply give the activations of the respective layer. The first term is the transposition of the outgoing weights of the layer multiplied by the error values of the foregoing layer, the layer in front. At this point, we can simply repeat these equations for however many layers we have left in our network. Once we have backpropagated through our network, we now subtract our bias and weight errors from our current bias and weight values. Importantly here, we first multiply all our errors by some value greater than 0 but less than 1, reducing the effect of this subtraction. This value is called our learning rate. Why we do this is to do with how partial derivatives work. For now, simply understand that the smaller proportion of our errors we subtract, the more accurately we train our network, and vice versa, the larger proportion of our errors we subtract, the less accurately we train our network. As such, in practice, we might only subtract 0.1% of our errors from our current values. When we need to very accurately train a network, we might subtract an even smaller proportion. And that's everything. You now know roughly how to do backpropagation. Thank you for watching.